Good day, ladies and gentlemen. I am Genevieve B. Portarques, and I will be sharing to you my understanding on the topic of rest energy, total energy, and relativistic and kinetic energy. So let's first discuss the following. The conservation of energy is one of the most important laws in physics. So, not only does energy have many important forms, but each form can be converted to any other. We know that classically the total amount of energy in a system remains constant. Relativistically, energy is still conserved provided its definition is altered to include the possibility of mass changing to energy. As in the reactions that occur within a nuclear reaction, relativistic energy is intentionally defined so that it will be conserved in all inertial frames, just as is the case of relativistic momentum. So as a consequence, we learn that several fundamental quantities are related in ways not known in classical physics. All of these relationships are verified by experiment and have fundamental consequences. The altered definition of energy contains some of the most fundamental and spectacular new insights into nature found in the recent history. So, let's first talk about kinetic energy. Kinetic energy is related to mass and speed by the familiar expression. The corresponding relativistic expression of kinetic energy can be obtained from the work energy theorem. This theorem states that the net work on a system goes into kinetic energy. So another is the energy equivalent to the mass of the particle is rest in an inertial frame of reference equal to the rest mass times and square of the speed of light. Another is the total energy is the system is the sum of the kinetic and gravitational potential energy, and this total energy is conserved in orbital motion. Objects with total energy less than zero are bound. Those with zero are greater and unbound. And rest energy is discussed by the following. The first postulate of relativity states that the laws of physics are the same in all inertial frames. Einstein showed that the laws of conservation of energy is valid relativistically if we define energy to include relativistic factor. So the total energy is defined to be E is equal to Y mc, where m is mass and c is the speed of light, while rest energy is E is equal to mc raised to 2. Then the kinetic energy is the energy of motion. Classically, kinetic energy has the familiar expression of m of 12 mv2, and the relativistic expression for kinetic energy is obtained from the work energy theory. This theorem states that the network of the system goes to kinetic energy. I mean.
Interesting thought, but there's no reason to expect that kinetic energy in mass over body times speed of light squared would have some special significance in Newton's law. Newton and his law didn't know about relativity or the constant speed of light. Newton's second law is an approximation that works at low speeds, and it isn't valid when we start thinking about speeds near the light. There are relativistic equations that are valid at any speed that can tell us what happens when Newton's laws fails. That's how you should calculate the actual velocity of the object. You can check the calculation yourself using any reference like that we can express for the kinetic energy and so for the velocity. Showing how objective velocity as a fraction of speed of light depends on the kinetic energy. It is noticed that the speed of light, the object would need to have infinite kinetic energy. When the kinetic energy is equal to mass of a body times the speed of light squared, the object velocity will be about 80 to 87% of the speed of light. That's all.